So let me just begin by briefly reviewing what we've done so far. So in my first lecture, I introduced the definition of topological quantum field theory. And an n-dimensional topological quantum field theory, it's various data, but in particular, it's something that assigns a number, a diffeomorphism invariant, to every closed manifold of dimension n. And if you want to compute that number, you might try to compute it by breaking your manifold up into pieces. Now, the definition of a topological quantum field theory that Atiyah gave in that definition, you have a limited freedom in how you can break your manifold up into pieces. You can break it up into pieces by cutting along closed submanifolds of codimension 1. But you would, of course, like to cut your manifold up into very fine pieces by, say, triangulating it. And if you want a set of rules that will tell you how to compute the invariant of a manifold that you've triangulated, then you need a more elaborate notion than the notion of a topological quantum field theory, something that I called an extended topological quantum field theory. And in order to define that notion, you need the language of higher categories. So in my lecture last Thursday, I talked a little bit about this language of higher categories. I introduced something which I called an infinity n category, which is, roughly speaking, a sort of higher category where all morphisms are invertible for k greater than n. And if you stuck around at the end last time, I gave a precise definition in the case n was equal to 1. And that precise definition can be generalized to higher n. Rather than considering simplicial spaces, you're supposed to consider multi-simplicial spaces that have a sort of n directions. I don't want to say very much about the definition. In this talk or in the next talk, I want to work with these objects in an informal way from now on. But another thing that I talked about on Thursday is one motivation for studying these infinity n categories, which again came from topological field theories, which was rather different from the motivation of wanting to think about extended topological quantum field theories. You might also want to think about topological quantum field theories that assign to manifolds invariants which are more sophisticated than just numbers. Invariants that are, instead of being numbers, are, for example, cohomology classes on some space. And in this context, you might want to the form that diffeomorphism invariant takes in a context like that is a little bit more subtle. Rather than just saying two diffeomorphic n manifolds get assigned the same number, you might want to say that the cohomology class that you get associated to a manifold M is somehow equivariant with respect to the diffeomorphism group of M. And in order to formalize that idea in a general way, you again might want to think about this, use the language of infinity n categories, but in this case, you're encountering higher category theory not because you want to include information about lower dimensions, but instead because you want to include more refined information about manifolds of dimension n. You want to think about their diffeomorphism groups and so forth. So these are two different ways that the higher theory of higher categories can sort of interact with topological field theories. And they're logically independent of one another, but they're compatible in the sense that we can contemplate both of these more elaborate notions of field theory simultaneously. So that's what I'd like to start out by saying something about today. I'd like to use this language of infinity n categories to describe the main object of interest to us in these lectures. So I'm going to describe something that I'm going to call board n. So this is going to be an example of an infinity n category. And I'm just going to describe it to you in an informal way. So its objects are going to be zero manifolds. So remember that in these lectures, the term manifold always means a compact, smooth manifold with an orientation. So one morphisms in this world, board n, are going to be Cobordisms between zero manifolds. In other words, one manifolds with boundary. Two morphisms are going to be given by Cobordisms between Cobordisms. In other words, they're given by two manifolds with boundary where those boundaries also have boundary, or two manifolds with corners. And now I'll write dot, 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 all the way up to n. Your n morphisms are supposed to be given by Cobordisms between dot, 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 where you have n levels of Cobordism, so I'll just describe that, summarize that by saying these are given by n manifolds with corners. And now, if we were defining the extended Cobordism category like I did in the first lecture, we would stop here. We would identify two n manifolds with corners if they were diffeomorphic to one another, and we wouldn't continue on. But Bord n, I want to go all the way to infinity by including information about diffeomorphisms. So now I'll say, in this world we also have n plus 1 morphisms, which are now given not by Cobordisms but by diffeomorphisms of n manifolds. And we have n plus 2 morphisms, which are given by isotopies between diffeomorphisms. And so on and so forth, out to infinity. So last time I told you that one of the ways that you can define an infinity n category, at least when n is equal to 1, is to think about categories where the Homs at the top level form not sets but topological spaces. So when n is equal to 1, an infinity 1 category you can define to be a topological category. That definition is not very convenient for actually working with and giving constructions and precise proofs of things, but it's very good for intuition. And similarly, an infinity n category, if you're comfortable with the usual notion of an n category where your n morphisms form sets, then you can think of an infinity n category as an object of the same type, except your n morphisms are forming topological spaces. And so another way of sort of summarizing this definition would be to think that your n morphisms are in this world form a topological space, and these are given by classifying spaces. For n manifolds with corners. So this is something that we'll come back to, particularly in the case n is equal to 2, where these classifying spaces are very well studied objects. For example, in algebraic geometry, where they look like moduli spaces or moduli stacks of Riemann surfaces. Okay, so this is an object which we might want to study. So how might we want to study it? Remember that in the first lecture I stated for you a version of the Baez-Dolan-Cobordism hypothesis which described n-dimensional extended topological quantum field theories. In other words, functors from the extended Cobordism category into another object of the same type. So let me recall that statement for you, and I'll state it in a more general form in this setting of infinity n categories. So first, let me make a remark, actually two remarks. So first of all, this is not just any infinity n category. It's what's called a symmetric monoidal infinity n category. It means that there's a tensor product operation on this. Tensor product given by disjoint unions of manifolds. And let me make a remark that you can give several variants on this definition depending on what kind of manifolds you want to talk about. So here I've indicated that I want to think about oriented manifolds, but you could think about manifolds with whatever your favorite kind of structure is. Manifolds without an orientation, or manifolds with a framing, or manifolds with a spin structure, or whatever you like. So let me just mention a variant. The framed Cobordism n category is defined similarly using what I called in the first lecture n-framed manifolds. That is, manifolds whose tangent bundles have been trivialized once you stabilize them to make them n-dimensional. Okay, so let me state the Cobordism hypothesis now. So let's see another object of the same type as n board, another infinity n category with a tensor product on it. So let C be a symmetric monoidal infinity n category. Then you can look at topological field theories with values in C. So let me define, and let's think about topological field theories that are only defined on n-framed manifolds. Taking values in C, the Cobordism hypothesis tells me that I can identify these, such a field theory with a single object of C, subject to a condition which I'll describe later on in this lecture, a finiteness condition called being fully dualizable. So this correspondence is given by taking a field theory, a functor Z, and assigning it the object of C, which is what Z does on a point. Okay, so what are my goals for this lecture? In this lecture, I would first of all like to tell you, make this statement more precise. I'd like to tell you what it means to be fully dualizable. I would like to tell you what happens if your manifolds are not framed, but if you considered the original board N that I defined over here. And if I have time, then I'll say how this relates to the Mumford conjecture. So first, let me make a remark. This is non-trivial. This statement is non-trivial even if n is equal to 1. So in my first lecture, I stated the Cobordism hypothesis, but just in the language of ordinary n categories. So when n is equal to 1, ordinary categories. And we were able to classify one-dimensional field theories very easily just by sort of eyeballing things. Remember that the one-dimensional Bordism category is pretty simple. The objects are just finite collections of points. Some have positive orientation, some have negative orientation. And the morphisms are just given by Bordisms. But there aren't many Bordisms to think about. There are just intervals and circles. And so everything is very explicit. And we were able to convince ourselves, or I tried to convince you, and hopefully I succeeded, that the Cobordism hypothesis is very believable when n is equal to 1 and C is an ordinary category. But when C is a infinity 1 category, things get a little bit more subtle. So I'd like to tell you a little bit about that subtlety. So this infinity 1 category, board 1, it's not so bad, too bad an object, but it's definitely not an ordinary category. So to see that, let's think about what Homs in board 1 are from the empty set to the empty set. So board 1, it's an infinity 1 category, and as I told you, you can think of it as a category. It has some objects, and then it has Homs, which are given by topological spaces. And what topological space is this? Well, this is a classifying space for closed one manifolds. So what's a closed one manifold? It's just a disjoint union of finitely many circles. So this space breaks up into connected components depending on how many circles you're looking at. And it contains a connected component corresponding to just one circle. And what does that connected component look like? Well, it's a classifying space for circle bundles. That's CP infinity. That space has the homotopy type of CP infinity, or in other words, B diff of a circle. And remember, all of my manifolds have an orientation, so when I say diff, I mean orientation-preserving diffeomorphisms. So this is a classifying space for oriented circle bundles. And this space, well, it's not so bad. It's a space that you can understand pretty well, but it's definitely not just a single point. So that's reflecting that board 1, while it's, as infinity 1 categories go, it's a pretty simple object, it's definitely not an ordinary category. Now suppose that we had a one-dimensional field theory, meaning a functor from board 1 into C. Well, we could think about what that functor did here. Remember, if this was a tensor functor, it would preserve the unit objects. So it would take the empty set as a zero manifold to the unit object in C. So this space of Homs from the empty set to the empty set would map to the space of Homs in C from the unit to itself. And in particular, we get a map from CP infinity into this relevant mapping space. So what is this map? How are you supposed to think about it? You're supposed to think this map is encoding what our topological field theory Z assigns to a circle. And last Tuesday, we computed that. We computed that Z of a circle, if say Z of a point was equal to an object X in C, then Z of a circle was this thing called the dimension of X. It was the morphism that you get by composing the co-evaluation map from the unit to X tensor X dual with the evaluation map from X tensor X dual back into the unit. So what does that mean in the present circumstances? Well, that calculation wasn't really telling you what this map from CP infinity in is. It's really telling you what this map does on a specific point of CP infinity. Because what does it mean to have a map from CP infinity into something? CP infinity is the classifying space for, say, rotation, the group of rotations acting on the circle. And so having this map from CP infinity into this mapping space, what it's telling you is, first of all, it's telling you what the base point of CP infinity goes to, which is this thing I called the dimension of X. But then it's also telling you that that dimension of X, Z of S1, is acted on by a symmetry group, namely the symmetry group of the circle. So if you want to give this field theory in this infinity 1 categorical sense, you have to not just say what it does, what Z of a circle is as a morphism in C, but you have to say how it's acted on by the symmetry group of the circle. And this calculation does not provide that, because how did we do this calculation? We took the circle and we broke it into two pieces, two half circles, and we thought of the circle as a composition of these two pieces. And as soon as you break a circle into two pieces, you've destroyed the symmetry. So this calculation is only going to tell you what this does on a single point of CP infinity. And in particular, you're probably not going to be able to prove the Cobordism hypothesis when n is equal to 1 using this sort of element-wise reasoning, just writing down all the manifolds that you can think of and seeing what everything has to do. You've got to be smarter than that. So you might say, well, we know where a point of CP infinity has to go. Why don't we just carry all of CP infinity to that point? In other words, why don't we just declare that this action of the symmetry group of the circle is going to be trivial on Z of S1? Well, that's probably not such a good idea, because if you believe the Cobordism hypothesis, then you believe that as soon as you fix an object X in C, there's a unique one-dimensional field theory which takes a point to X. And that one-dimensional field theory will dictate to you a specific action of the circle group on the dimension of X. And that circle action is typically not going to be trivial. It's typically going to be something interesting. So let me just give an example. So to give an example, I have to give you an infinity 1 category C. So let me describe my infinity 1 category C. My objects are going to be associative algebras over the complex numbers. And my morphisms, well, Homs in C from A to B, let me just say this a little bit informally, these are going to be given by chain complexes of A-B bimodules. Now, I'm describing an infinity 1 category, so I also need to tell you what the n morphisms are for n larger than 1. Or in other words, I need to tell you how to make the set of chain complexes that I described here into a space. So let me not describe that. What you really want to do is form some kind of classifying space where say, paths in that space, points in your space correspond to chain complexes, and paths somehow correspond to quasi-isomorphisms of chain complexes. Let me not go into the details. So this is let me remark that every object of C is fully dualizable. I haven't told you what that means yet, but what it amounts to in this case is that every object of C has a dual. And the dual of an algebra A is just going to be the opposite algebra, the same vector space with the multiplication switched. And that means that if I give you an object A and C, if you believe the Cobordism hypothesis, then you get a field theory Z. And if you evaluate Z on a circle, well, a circle is a Bordism from the empty set to the empty set. And so what you're going to get here is a morphism in C from the unit object to itself. Now the unit object in C, tensor product I should have mentioned, is just ordinary tensor product of algebras. The unit is just the complex numbers. And so a HOM from the unit object to itself is just a chain complex of C bimodules. In other words, a chain complex of complex vector spaces. And what is that chain complex? Well, it's a chain complex which computes the Hochschild homology of the algebra A. And now the fact that this is acted on by the circle, that's sort of a classical fact that Hochschild homology of an algebra carries some kind of circle action. And classically, you might say this comes from the fact that you can compute this Hochschild homology using a cyclic bar construction. But it also, that circle action also comes about from this general formalism having to do with the Cobordism hypothesis. And that circle action is typically interesting. Okay, so now what I would like to do is say a little bit about what it means to be fully dualizable. So let's start with the case, start with the ordinary category of vector spaces. So if C is the category of complex vector spaces, we want to say that an object V in C is fully dualizable if V is finite dimensional. We're all familiar with the category of vector spaces, and we know that the natural finiteness condition that you can put on a vector space is that it should be finite dimensional, or that it should have a finite basis. So we'd like to generalize that to a finiteness condition that makes sense in any symmetric monoidal infinity n category. So the first thing we might try and do is describe what it means to be finite dimensional in purely category theoretic terms. We don't want to talk about bases of vector spaces or anything that's specific to the definition of a vector space. We just want to talk about generalities that we can formulate in terms of the category of vector spaces.
That statement's if and only?
Yes, if and only if. So I've sort of already given it away with this terminology of fully dualizable objects. You can single out the finite dimensional vector spaces by the fact that they have a good theory of duals. So what do I mean by that? So let V be a vector space. For any vector space, I can define its dual space. V dual, this is the space of linear maps from V into the complex numbers. And for any vector space, there's a map from V tensor with its dual space into the complex numbers. And moreover, the dual of V is universal with respect to the fact that there exists such a map. But usually the relationship between V and its dual is asymmetric. You know, if V is, say, countable dimensional, then V dual will be uncountable dimensional. It'll be a lot bigger. But for finite dimensional vector spaces, this relationship is symmetric. So what's special about finite dimensional vector spaces is that if V is finite dimensional, that there's also, so let me call this map evaluation, there's also a canonical map from the complex numbers into V tensor V dual, which I'll call co-evaluation. If I think of V tensor V dual in the finite dimensional case as the space of endomorphisms of V, well, this is the map which takes the trace of an endomorphism, and this is the map which includes the identity as an endomorphism. And now, well, so far I haven't said anything, because there's always a map from C into V tensor V dual. You can take any map. But what I want to say is that this co-evaluation map has some good features. So these are compatible in the following sense, that if you take V mapping to V tensor V dual tensor V by, say, identity tensor co-evaluation, and then you map that by evaluation tensor the identity back into V, this is the identity map, and similarly for V dual. Are the identity maps. So if you're not familiar with this sort of formalism and you're bored during this lecture, maybe a good exercise would be to check that these conditions are satisfied if V is a finite dimensional vector space and these maps are defined in the way that I described. So in fact, this is part of a general formalism of duals which makes sense in any symmetric monoidal category. Namely, you'll say that an object V has a dual if there's another object, V dual, and there are evaluation and co-evaluation maps, like so, that satisfy these conditions. So let me just summarize by saying, generalizing, you get a theory of dual in any category, or any symmetric monoidal category. And just like in the category of vector spaces, in the general case, it turns out that if V has a dual, then that dual is determined up to canonical isomorphism. So all of this data is essentially unique if it exists. We can define this notion in any ordinary category, and more generally, we can define it in any infinity n category. With tensor products, and when I say that, I don't mean that you need to develop a much more elaborate theory of duality. I mean that in a very naive sense, by passing to the homotopy category. In other words, we'll say that an object of an infinity n category has a dual if there's another object, which we call its dual, and there are one morphisms, evaluation and co-evaluation, such that these equations hold up to homotopy, or up to isomorphism. So now I can give you part of the definition of being fully dualizable. Definition. Let C be a symmetric monoidal infinity 1 category. An object X in C is fully dualizable if it is dualizable. In other words, if there exists a dual and maps like this such that these conditions are satisfied. So now we already have a more precise version of this Cobordism hypothesis when n is equal to 1. What we're saying is that giving a one-dimensional field theory with values in C is equivalent to giving just an object of C that has a dual. So what if n is not 1? Well, what I just said immediately indicates that just being dualizable is not going to be enough, because just knowing that an object has a dual in C, that's enough to buy you a functor from the board 1 into C. But if you have no further conditions, then there's no way you're going to promote that to a functor valued on this larger category, board n. You're going to need some stronger finiteness condition on an object x in order to get this field theory to be defined on manifolds of higher dimension. So what kind of finiteness condition do you want to contemplate? Well, it's going to be finite. We're going to contemplate some finiteness conditions which are analogous to having duals, or maybe I should say generalize the idea of having duals. So I need to embark on a digression. So last Thursday, I talked about higher category theory. In particular, I introduced the notion of a two-category, but I maybe neglected to give you the most basic example of a two-category, namely the two-category of categories. So one example of a two-category is something I'll denote by cat. The objects are categories. The morphisms are functors. And the two morphisms are natural transformations between functors. And it turns out this is an example of a two-category that naturally comes to you as a strict two-category. The composition of functors is just associative on the nose. So this happens to be strict, though don't take that as an indication of anything. So so what's the point of category theory in mathematics? So one argument that you can give for category theory is that it gives you a way of recognizing that a lot of constructions which come up when you're talking about different kinds of mathematical objects have something in common. Like you notice that you have this idea of Cartesian product, and you can take the Cartesian product of manifolds and Cartesian product of abelian groups and so on and so forth. And although the kinds of objects that you're thinking about are very similar, the formalism of what it means to be a Cartesian product the objects are very different, but the notion of Cartesian product in each of those cases is the same. So you can sort of axiomatize out the essence of what's going on by saying in each case you have a category, and there's a general notion of Cartesian product in any category. So if you wanted to justify higher categories along the same lines, you might say one of the points of higher categories is to take some examples of higher categories that we know, like the two-category of categories, and extract out some formal features which might make sense in more general two categories. So I would like to do that now, where the formal features that I would like to discuss, or the situation I would like to describe, is the theory of adjoint functors between ordinary categories. So let me just recall, if C and D are categories, and we have functors f from C to D and g from D back into C, these functors are said to be adjoint to one another if there are natural bijections Homs in D from f of an object little c into an object little d can be identified with Homs in C from an object little c into g of big little d. So here natural means it's functorial with respect to the choice of object little c in C and little d in D. So in this case, you say that F is the left adjoint and G is the right adjoint. So adjoint functors come up all the time in all kinds of mathematics, and you might say adjoint functors are an important concept in the theory of categories. So what I'd like to explain now is that this notion of adjointness is really a notion which is which you can define not just for this particular two category of small categories, but it makes sense in any two category. So in order to do that, I'd like to take this definition which I've given here and describe it in a more two-categorical way. Like here I'm using sort of element-wise reasoning. I'm using the details of what it means to be an object of cat. An object of cat has objects little c, and I'm playing around with those objects. I'd like to recast this definition in a way that doesn't use those internal details. So suppose that we have a bijection like this. How is it implemented? Well, note that by taking D to be f of c, and we have the identity element, the identity map from f of c to itself. And that lives in Homs from f of c into D. And if we had this bijection, that would give us a Hom from C into G of D. In other words, I have a natural map from C into G composed with F on the object C. And this is supposed to be functorial with respect to my choice of C. So I can say that instead of saying I have such a map for every C, I'll say I have a natural transformation, i.e., we have a natural transformation U, which goes from the identity functor from C to itself to this composition G composed with F. Now U encodes a lot of what's going on here. Using U, we can use U to recover maps. Well, let's say in general we have a Hom in D from f of c into some object D. We could then apply our functor G to get a Hom in C from G composed with F of C into G of D. And then if we had our natural transformation U, we could compose with that to get a Hom in C from C into G of D. So just having a natural transformation U like this gives us a candidate for what these bijections should be. They should be given by that process that I described over there. Now, of course, for a general U, natural transformation like this, the map that I define might not be a bijection. So to guarantee that this is a bijection, what I want is something that lets me define the inverse map. And just like the collection of all of these maps was encoded in a single piece of data U, the collection of maps going in the opposite direction can be encoded in a single natural transformation as well. You want a map, something I'll call V, from F composed with G, the identity functor from D to itself, which induces the inverse maps. So anytime I give you a natural transformation U, I can define a map that goes from the left-hand side to the right-hand side. Anytime I have a natural transformation V like that, you can define a map that goes from the right-hand side to the left-hand side. Now, in general, those maps won't be inverse to one another. You have to require that U and V are somehow related. So how should U and V be related? So U and V need to be related in the following way. First of all, if I start with the functor f, and then I apply my my unit map U, I'll say U cross the identity, that maps into f composed with G composed with f. Identity cross U. And then I can apply my natural transformation V cross the identity to map back into f. This should be the identity on f. And similarly, there's a composition here which should be the identity on G. So what's the upshot of this whole discussion? The upshot is that the theory of adjoint functors can be described in an entirely, in a way that's entirely internal to this two-category cat. What is an adjunction? It means that you have a pair of categories, that's objects of cat. You have a pair of functors, f and g. Those are one-morphisms in cat. You have a pair of natural transformations, u and v. Those are two-morphisms in cat. And you have these two equations. So that's a notion which can be exported now to any two-category we like. We can talk about adjoint one-morphisms not in the two-category of categories, but in any two-category that we're interested in. So another upshot of this discussion is that these equations which I wrote down over here should look familiar. We were discussing duals of objects in a monoidal category just a minute ago, and this is very similar. The compatibility that U and V have to satisfy here is analogous to the compatibility that the evaluation and co-evaluation map have to satisfy in order to say that an object has a dual. Okay, so the moral of this discussion, I guess, is that adjoints are like duals, or we can be more precise than that about the relationship between adjoints and duals. Let me give an example. Let C be a monoidal category, or let's say symmetric monoidal. Then you can define a two-category, which I'll call B of C. This is a two-category which has a single object. Morphisms from this single object to itself, well, I'm in a two-category, so the morphisms are supposed to form a category. And that category will be C. And I have to tell you how to compose morphisms. And that, I'm going to compose them by tensoring the corresponding objects in C. So this actually establishes a dictionary. Giving a two-category with a single object, well, you just have to specify the category, which is Homs from that object to itself, plus how you compose those Homs, which is some sort of tensor product on the original category. So under this dictionary, the theory of duals in C goes over to the theory of adjoints in BC. So given a pair of one-morphisms, let's say F from star to star, and G from star to star going in the other direction, are adjoint in the sense that I just gave the definition of in in BC if and only if F and G are dual in the category C. Remember that 1 morphisms in BC can be identified with just objects in C. So again, this is just an exercise in unwinding and understanding the definitions that I've given you so far. If you just take the definition of what it means to be adjoint in this 2 category and spell it out, well, you need these natural transformations U and V, which correspond to the evaluation and co-evaluation maps in the previous discussion, and you need these relations which immediately reduce to the relations that evaluation and co-evaluation are supposed to satisfy. So the moral of this discussion is that the notion of having duals, which is the way that we wanted to encode finiteness conditions in an abstract categorical setting, is really a special case of this theory of adjoints, which makes sense in a higher categorical setting. Okay, so now let me get to the point. So end digression. So let me introduce a definition. Just like we had this notion of having duals in a symmetric monoidal category, and we could immediately export that to an infinity n category by passing to the homotopy category, we can do the same with this theory of adjoints. Given if C is an infinity n category, we say that a pair of morphisms F from X to Y and G from Y to X are adjoint if, well, one way to say it is that this data defines an adjunction in the underlying 2 category that I get by sort of throwing away all of the higher information in C. But more concretely, if there exists a map U from the identity to G composed with F, these are 2 morphisms now, and V from F composed with G into the identity, such that these axioms there hold up to isomorphism. Now, in general, just like not every vector space has a dual, if you're working in a 2 category, not every morphism has an adjoint. But it's convenient when morphisms do have adjoints. And so let's introduce a definition which requires that. So definition, an infinity n category C has adjoints. Well, I just want to say, what I want to say is that all morphisms at all levels of C have adjoints, provided that that makes sense. So when does that make sense? Well, it doesn't make much sense to demand this for n morphisms in the category C, because if I had an n morphism in the category C and I wanted an adjoint for it, well, these U's and V's would have to be n plus 1 morphisms. But n plus 1 morphisms in C are invertible, so these would be invertible, and these would tell us that in fact the adjoint was an inverse to F. So that's too strong a demand to make it level n, but it's a sensible demand to make it every level below n. So let me give, more precisely, you can give this as an inductive definition. So first of all, we'll say this condition always holds if n is equal to 1. If n is equal to 2, we'll require that every morphism in C has a left and a right adjoint. And if n is greater than 2, we demand that, well, let me say, if n is greater than or equal to 2, we'll demand that all of the morphisms have adjoints. And if n is greater than 2, we'll also demand that that Homs in C between any two objects has adjoints, where this is now an infinity n minus 1 category. So unwinding this, this just means that all morphisms at all levels except the top level are required to have adjoints. And now, definition. Let C be a symmetric monoidal infinity 1 category. Infinity n category. That is an infinity n category equipped with tensor products. So now it makes sense to talk about duals for objects. We'll say C has duals if, first of all, C has adjoints, and second of all, every object of C has a dual. And it's not that random to string these two conditions together because, as I mentioned a little while ago, having duals is really a special case of something else having adjoints. So this is equivalent to saying that this category, this infinity n plus 1 category that I get, that I indicated earlier called BC, that this has adjoints. Because here I've taken the objects of C, I'm interpreting them as one morphisms, and requiring that my objects have duals is equivalent to requiring that those one morphisms have adjoints. All right, so now let me, it's too bad I erased the Cobordism hypothesis. So what does the Cobordism hypothesis say? It says, so this is a slightly modified version of the original Cobordism hypothesis. Let's assume that C has duals. That's a strong finiteness requirement on C. So for example, the category of vector spaces does not have duals because not every object in the category of vector spaces has a dual. That's only true, only the finite dimensional vector spaces have duals in the sense of the categorical definition that I gave earlier. So the category of all vector spaces doesn't qualify here, the category of finite dimensional vector spaces does. But if we restrict our attention to the case where C has duals, then we don't need to require any finiteness conditions on our objects. Namely, if the category C has duals, then giving a topological field theory with values in C is just equivalent to giving a single object of C. So now you might say, what if C doesn't have duals? Well, let me just give an example of a category with duals. The frame Cobordism category has duals. The dual of any manifold, or more generally the adjoint of any manifold, is just given by the same manifold but sort of read in a different direction. You know, if you have a morphism in board n, it's given by some Cobordism between two manifolds. If you just change the orientation of that manifold and read it in the other direction, then it's a Cobordism. Cobordism from m to n becomes a Cobordism from n to m, and that becomes an adjoint in the sense that I described here. So this is an example of something with duals, and the upshot of that is that there's no real loss of generality when studying topological field theories in restricting your attention to the case where C has duals. Namely, any tensor functor from the frame Cobordism category into C is going to land in the part of C which has duals. So let me make that a little bit more precise.
For a frame manifold, you're saying there's an opposite framing?
There's an opposite framing because, well, you just change the sign of one of the basis vectors for the tangent bundle, namely the one that corresponds to the direction in which you're taking the adjoint. So note that for any C, so let's say for any symmetric monoidal infinity n category C, there exists a largest, I'll put this in quotation marks, subcategory, C fully dualizable, contained in C, such that C fully dualizable has duals. So what do I mean by largest? And what do I mean by contains in? Well, I mean it's a category which maps to C, and it's universal among infinity n categories with duals that map to C. In what sense is it a subcategory? Well, you can give an explicit construction of it. Roughly speaking, you take C and you throw away all the stuff which doesn't have adjoints. So for example, you might start with the n minus 1 morphisms. Some of those won't have adjoints. Throw those away. Then n minus 2 morphisms, look for those which have adjoints, throw away the ones which don't, and so on and so forth, until eventually you throw away the objects which don't have duals. And at the end of that process, you're going to be left with something, you're going to be left with something which has duals and which is in some sense contained in C. And now so largest being that universal property that I suggested means in particular that tensor functors from board n framed into C are the same as tensor functors from board n framed into the fully dualizable part of C, which by the Cobordism hypothesis, as I've stated it here, is equivalent to the collection of objects of C fully dualizable. So if you want to, so now that will recover the Cobordism hypothesis in the way that I stated it previously if we make the following definition. An object X in C is fully dualizable if it belongs to C fully dualizable. All right, so let me just say a few words so that you get a feel for what this condition is. This condition of being fully dualizable. So,
are you going to say that's an isomorphism of what kind of mathematical objects?
This is an equivalence of infinity groupoids. Or, there's no loss in content in just saying it induces a bijection between isomorphism classes of functors and isomorphism classes of objects. You can get from there to an equivalence of infinity groupoids by replacing C by some functor category. Okay, so let me make a few remarks about this notion of fully dualizable. So, examples. When n is equal to 1, what is this? So suppose I have a symmetric monoidal infinity 1 category. What is its fully dualizable part? Well, for an infinity 1 category to have duals, that's no condition at the level of morphisms. It's just the condition that every object have a dual. So this long process that I described here actually takes place in just one step. You throw out all the objects which don't have duals. And so we recover the definition that I gave earlier. An object X in C is fully dualizable if C is dualizable. So when n is equal to 2, you can also spell this out in fairly concrete terms. An object X in C is fully dualizable if, well, first of all, X should be dualizable. That's obviously necessary. But now we need more. Because if you'll remember, what does it mean to be dualizable? it means that there's another object x dual, and there's a co-evaluation map from 1 into x tensor x dual, and there's an evaluation map from x tensor x dual into 1. And now just because x is dualizable as an object of C doesn't mean that it's going to be dualizable as an object in the subcategory of C that I get by throwing out one morphisms that don't have adjoints. In order for this duality data to give me an object in the fully dualizable part of C, these evaluation and co-evaluation maps have to themselves have adjoints. So condition 2, let me write the evaluation and co-evaluation both have left adjoints. Now, it's not obvious that that's enough, but it's at least, well, let me say, this is true if and only if these conditions are satisfied. The only if part of this assertion is clear. If x is going to be fully dualizable, well, it had better be dualizable, and this evaluation and co-evaluation map, they had better belong to the fully dualizable part of C also, so they need to have left adjoints. Now, it's not obvious that this is sufficient. Just because evaluation and co-evaluation have left adjoints, how do you know they have right adjoints? But this turns out to be sufficient. You can sort of construct the right adjoints to the evaluation by playing around with the left adjoint to the co-evaluation. Now, when n is large, example n greater than 2, more complicated. The conditions have a similar flavor. First of all, x has to be dualizable. It needs evaluation and co-evaluation maps need to have left adjoints. That means that we have some adjunctions, which means we need unit and co-unit maps for those adjunctions, which are two morphisms in C. And then those two morphisms themselves need to have adjoints. And if you spell it out, well, you might think a priori you need to check an infinite amount of stuff. It turns out that you only need to check a finite amount of stuff, but it's still enough stuff that I would rather not write it down at the board. OK, so I've talked for about an hour, and I haven't gotten to what I said I was going to get to. Maybe we should take a 2 or 3 minute break, and after the break I will tell you what happens to this statement when we replace the framed Cobordism category by some other kinds of manifolds.
All right.
Let M be a manifold of dimension d less than or equal to n. An n framing of M is an isomorphism of the tangent bundle of M stabilized by adding a trivial bundle of rank n minus d with a trivial bundle of rank n. So here, when I underline r to the n, I mean take r to the n and make it a vector bundle on the manifold M. So this framed Cobordism category, remember, the way that it's defined is it's made out of manifolds where all of the manifolds are required to be equipped with this, this structure, the structure of an n framing. So now observation. The group ON acts on n framings of any manifold. Namely, it acts by composing these isomorphisms with the action of the orthogonal group on this trivial bundle r to the n. That means that we get an action of the orthogonal group on this entire Cobordism category, board and framed. And now let's go over to the Cobordism hypothesis. So the Cobordism hypothesis says if C has duals, then functors from this Cobordism category into C are equivalent to objects of C. So now we have an action of the orthogonal group on this framed Cobordism category. And we can, by transport of structure, we get an action of the orthogonal group on the objects of C. So now it becomes important how I've answered Dan's question. Dan asked, what is that an equivalence of? How do I want to think about it? Well, this turns out to be an infinity groupoid. In other words, I can think of it as a topological space. And this is a topological space. This is the underlying infinity groupoid of C that I get by throwing away the non-invertible morphisms at all levels. And the claim is that that topological space, it can be realized. It's homotopy equivalent to something which carries a natural action of the orthogonal group. So let me give some examples to make this ON action sound more believable. Let's start with the example when n is equal to 1. So C has duals. That means that every object of C, since C has a dual, X dual, and so we have a construction which takes every object to its dual. And you would expect that this should, in some sense, be an involution. And in fact, it is. And that sense is made precise by this Cobordism hypothesis. There's an action of O of 1 on the space of objects of C. And what that action does is take every object to its dual. O of 1 on the space of objects of C. And now, why did I write objects of C and not just say there's an action of O of 1 on C? Well, here I want to be careful. This construction, which takes X to its dual, that's not a covariant functor from C to itself. It's a contravariant functor. In other words, if you want to think of it as a functor, it's a functor from C to its opposite category. So the group O of 1 is not acting on the category C, or at least it's acting in some sort of a twisted sense, which I don't want to contemplate here. But that twisted action does give me an action of C on the underlying infinity groupoid, or in other words, the space of objects. So let me give another example. So let's say that C is an infinity groupoid. So remember that every infinity groupoid can be thought of as a topological space. So I'll say C is pi less than or equal to infinity of X, where X is some topological space. And now let's say that C has a symmetric monoidal structure. In other words, there's some sort of operation, multiplication on C, which is commutative and associative up to coherent isomorphism. This translates into topology by saying that X is what's called an E infinity space. So if you haven't seen this notion before, the E here stands for everything. And the idea is X is equipped with some sort of multiplication, which it's not commutative and associative on the nose, but it's commutative and associative up to homotopy and up to all higher homotopies that you could ever think to write down. It's sort of commutative and associative in the best possible sense that you can make sense of purely homotopy theoretically. But now, if C has duals, what does this translate to? Well, first let me remark that just knowing that X is an E infinity space, it has a multiplication which is commutative and associative up to homotopy. That means that if I pass to pi naught of X, I get a multiplication which is commutative and associative on the nose. So pi naught of X is a commutative monoid. Now what does it mean for C to have duals? Well, first of all, it has to have adjoints. But since C is an infinity groupoid, all of the morphisms at all levels of C are invertible. So an invertible morphism always has a left and right adjoint, just given by its inverse. So there's no condition at the level of morphisms there is a condition at the level of objects. Every object of C has to have a dual. But since C is a groupoid, having a dual is, again, the same as having an inverse. And if you translate that into homotopy theory, this is equivalent to saying that X is group-like, or what's called a group-like E-infinity space. In other words, that pi naught of X, which we already knew to be a commutative monoid, is an abelian group. And now, homotopy theorists will tell you that as soon as you've got a group-like E-infinity space, it has a lot of structure. This is equivalent to saying that X is an infinite loop space. So in particular, we can write X as the nth loop space of some space Y. Or not, let me say what I mean by an nth loop space a little bit more precisely. The nth loop space of Y is maps from an n-dimensional disk into Y that carry the boundary of that disk to some base point of Y. All right, so now what does the Cobordism hypothesis say? Or sorry, what is this observation that O of n acts on any the objects in any infinity n category with duals? So what is the space of objects of C here? Well, that's just X. So the claim is that X has a natural action of the orthogonal group O of n, and that's true for any n. And what is that action? Well, that action is written here on the board, or it's clear from this way of writing X. If X is the nth loop space of a space Y, it's maps from an n-dimensional disk into Y that do something on the boundary of that disk, and the orthogonal group acts on that disk, preserving its boundary. So this has a natural action of the orthogonal group O of n, and that gives you an action of the orthogonal group n on X. You can summarize this for those who are familiar with with some algebraic topology, that if C is an infinity groupoid, the action of O of n is via the J homomorphism. Okay, so here are two cases in which this O of n action is something that you can sort of understand in more concrete terms. If you're actually doing homotopy theory, the O of n action comes from the J homomorphism, and if n is equal to 1, then the O of n action is just replacing every object by its dual. And in the general case, well, for example, if you want to know how just a small piece of O of n looks, like if you want to know how O of 1 sitting inside O of n acts on an infinity n category C with duals, well, O of 1, the action of that piece of O of 1 is going to be dictated by this. It's going to replace every object by its dual. But what this action of O of n is saying is that actually when you take a dual, you can imagine that you could take duals in many different directions if you were in an infinity n category. And the duals that you take in many different directions would sort of have various relationships to one another that are reflected in the way all of these different copies of O of 1 sit inside O of n. Okay. So now suppose G is an arbitrary topological group with a representation into the orthogonal group O of n. Then, first of all, we can define the notion of G structure on a manifold, i.e. this is a principal G bundle P over our manifold such that if I form the associated vector bundle using this representation, this gets identified with the tangent bundle of M. And if this isn't in dimension n, I should stabilize to put it in dimension n. And now using these manifolds, we can define what I'll write as board NG. This is the Cobordism theory. It's an symmetric monoidal infinity n category that's defined like board n, except rather than using oriented manifolds or framed manifolds, we're going to use manifolds that are equipped with a G structure in this sense. So some examples. Board SON n. This is what I originally defined, where I just required all of my manifolds to have an orientation. Or if I put the trivial group here, then this is board n framed. But I could put other things here. I could put, say, spin n, and this has something to do with spin manifolds, and so forth. And don't be misled by the fact that all of the examples I've given, I've taken the group G to be a Lie group. There's not that many Lie groups, but there's plenty of topological groups with homomorphisms to O of n. And that lets you contemplate plenty of different kinds of structures in this sense. So what else do we get? Well, I said that O of n acts on the space of objects of a symmetric monoidal n category with duals. So if I have a homomorphism from G into O of n, then G acts on the space of objects of C, if C has duals. So now we can state the Cobordism hypothesis for G manifolds as follows. If C has duals, then we could consider a field theory defined on G manifolds, taking values in C. Well, any field theory defined on G manifolds is in particular defined on framed manifolds. Any framed manifold, we can give a G structure for any G. And therefore, we should get an object of C. But that object of C will have some additional structure if I can extend my field theory to a field theory of G manifolds. What that extra structure is that it's actually a fixed point with respect to the action of the group G on the space of objects of C, or maybe I should say a homotopy fixed point. A fixed point in the homotopy theoretic sense. In other words, this can be identified with the space of maps, which are G equivariant from EG into this space of objects. Of C, where EG denotes a contractible space with a free G action. This is, in other words, you're supposed to imagine EG is really a point, and you're giving a G equivariant map from a point into something, and that means that where that point goes has to be a fixed point with respect to the action of G. But this notion of homotopy fixed point is a replacement for that, where you don't demand that it's actually literally a fixed point, but that it's only in some sense a fixed point up to coherent homotopy. So what is this saying? Let's just give an example when n is equal to 1. And let's say G is the entire group O of 1. So maybe I should have given one more example there. Board n O of n in general. This is the Cobordism theory of unoriented manifolds. If G is equal to O of 1, then what we're saying is that a field theory one-dimensional field theory, but defined for unoriented manifolds, is the same thing as giving a object of C, which is a fixed point with respect to this involution that I get that carries every object to its dual. So I'll just write this informally. This is the space of symmetrically self-dual objects of C. So if I have an object x in C, this action of O of 1 takes that object to its dual. So if you're going to be a fixed point in particular, you have to have an equivalence of x with its dual. And that equivalence is determined by giving some sort of pairing, x cross x, into the unit, which is non-degenerate in the sense that it identifies x with its dual. But being a fixed point actually means a little bit more than that. It's not just being a fixed point in a set theoretic sense. You need to be a fixed point in a homotopy theoretic sense, which means that this pairing, in concrete terms, that means that this pairing should be symmetric. So if C is the category of complex vector spaces, the example that we started with, this says that C should be our object is a finite dimensional vector space with a symmetric bilinear form. Yes, non-degenerate. Okay, so now I would like to give you more examples, but it's difficult to give more examples because this is the only case really in which I've made explicit what the O of n action is doing. So if I wanted to tell you, for example, what it meant in dimension 2 to have a field theory defined for oriented two manifolds, I would need to understand how the group SO2 is acting on the objects in a symmetric monoidal infinity 2 category. And yeah, I should stop here, but maybe we'll pick that up next time. Thank you.